So welcome back to the Friday lecture in Physics 4480. We are going to today to continue along the lines we did yesterday with the FCI calculations. And just to quickly give you a reminder of where we were yesterday. So what we had done was to rewrite the ansatz for a given state in terms of the computational basis. In our case, if we now look at the ground state, so this should in principle be the exact ground state, which is an expansion in terms of the orthogonal computational basis of Slater determinants, which in turn are constructed from a single particle basis. And in our case, what we have is a coefficient C0 multiplied with what we have as an ansatz for the ground state, plus the various particle hole terms. So we just reordered all the configurations in terms of particle hole excitations. And this is multiplied with a coefficient, an unknown coefficient, Ci of A. And then we have the next term, which represents, so this term here is a one particle, one hole excitation. And then we have a two particle, two hole excitation. So we would have a coefficient Cij, AB, and then we have the creation and annihilation operators of AB, dagger, AJ, AI of phi 0. And this continues up to the last term. So this is a two particle, two hole term, plus plus, till we have the last term, which now represents simply n particle, n hole excitations. And that's the total number of particle hole excitations which we can make. Now, what we did was to rewrite this in a more compact form. So we wrote it like in sum over all possible particle hole configurations. And then we have the coefficient CH of P. And then we had this shorthand notation of H of P here. And where this H of P could represent a specific one particle, one hole, two particle, two hole, etc., etc. And then we took this pH and transformed that one into just one single symbol, an I. So this I represents a specific configuration. So you could just think of this as a vector which contains configurations, and that points to specific particle hole excitations. So every element here now refers to a specific particle hole excitation. And then what we did then was to simply rewrite these states of H of P. They were rewritten as a phi of I, like this. And then we had the coefficients CHP. These are the overlap coefficients, which we in principle don't know. And they were simply rewritten as a C of I here. And then what we ended up with is an eigenvalue problem, where we had a sum over the j's of the CJs, and then we had the H of the IJ, which is equal to the eigenvalue lambda of C of I. So this is a standard eigenvalue problem. And in this case, we had actually assumed that this overlap matrix, which we defined as an Sij, was simply given by a Kronecker delta, delta Ij. So this is the assumption. And in most cases, we will always end up having a basis which is orthogonal. That's often the kind of starting point which we have for most of the many body physics methods which we're dealing with. So, and then we could rewrite everything in terms of these matrix elements. So these matrix elements A, H, I, J, they were simply the transition matrix elements, just matrix elements, as we're going to call them. At the end, we just call them matrix elements. So this should be an I here, and J. And in one of the exercises in the beginning of the semester, we showed actually how to calculate these matrix elements. And these can then be tabulated in terms of the two-body and one-body matrix elements. And they would involve a sum, or they could just be a single matrix element. So as an example, when we looked at the overlap between this state and the state IA, this one, that reduced to a matrix element, which was given by this operator F, which we defined, and the state A. So this is just an example of the matrix elements which we get. Now, when we do this FCI calculation, or full configuration interaction calculation, we can make truncations. We could even say now that we are only looking at specific matrix elements or specific states, so we can actually leave out some of them, and that gives a truncation to the FCI calculation. But let's now rewrite the full problem when we are going to set up, because we can use Wick's theorem to set up these matrix elements easily. So these matrix elements here, matrix elements which we calculated last week using Wick's generalized theorem. And since these will contain either one-body operators or two-body operators, or one-body and two-body operators, we can easily set them up. And the thing which remains then is simply to diagonalize the matrix. But let's set up the matrix now, because what we are going to do is to look at what I called yesterday a less practical way of solving the problem. And the reason for why we're going to do that is that this links well with what is coming. So if you can diagonalize, if you can define your Hilbert space in terms of something which can be diagonalized, then you diagonalize, period. However, since this Hilbert space in principle is infinitely large, that means that we often end up with approximative methods. And Hartree-Fock theory, which we're going to see next week, is an approximative method. Many-body perturbation theory is an approximative method. Copper cluster theory, all the many-body theories are approximative methods. Then the quality of a given method depends on how well you can assess the error for what you leave out. So let's now rewrite this problem, which you see here, this specific problem here, this eigenvalue problem, in terms of the explicit matrices with their specific components. So what we did yesterday, and this is basically where we ended. So what we had, when we are setting up the matrix, I'm just setting up the blocks of matrix elements. So there's going to be a block with one particle, one hole excitations. There will be a block with two particle, two hole excitations, three particle, three hole excitations, and so on, up to the final block, which will now contain n particle, n hole excitations. So that will be the column elements of the matrix, which we normally call the Hamiltonian matrix. So this matrix is typically called the Hamiltonian matrix. And I guess when you took a course in quantum mechanics, this was defined in some of the basic courses, right? So it's a Hamilton. So this way of rewriting Schrödinger's equation, this is nothing but a rewrite where you made an expansion in terms of a basis, and these are the expansion coefficients. This way of rewriting it leads to this matrix, which is called the Hamiltonian matrix. And as we have seen now with Wick's theorem, we can easily calculate these matrix elements. And remember now that these matrix elements, they reduce into one-body terms and two-body terms, but these are many-body transition matrix elements. Because you start with a many-body state here, you have a two-body or three-body operator, and you end in a many-body state. So we would call this a many-body Hamiltonian matrix element, because your state here is a many-body state. But it's not the eigenstate of H. The eigenstate of H, if we are looking at the ground state, is given by this quantity, which is a linear expansion of all these other guys here. So when we did this, we have the similar row elements. So phi 0, this is a ground state, which we normally also call zero particle, zero hole excitation. And then you have defined an ansatz for the ground state of the system, which means that you fill, for fermions, you fill all single particle states up to a given level. If you're having bosons, you could place all the bosons in the first single particle state, and just fill that up, because that is a state which you assume is the one which is going to give the largest overlap with the exact ground state. And then we just continue like this: one particle, one hole, two particle, two hole. Let me just correct it here. So this is a two particle, two hole, three particle, three hole. I have a little bit more space here, four particle, four hole. And this goes all the way down to n particle, n hole. And then this matrix here is then multiplied with these coefficients, which are the eigenvectors in our case. So I'm just writing this multiplied with these different coefficient matrix elements. This is a C, one particle, one hole, C, two particle, two hole, etc., all the way down. And then you have a lambda, and then it's multiplied with this vector with the unknown coefficients. And yesterday we actually wrote this as a vector. So this is just multiplied with this vector C. And then we had all these elements. So this becomes actually the Hamiltonian matrix. And now I'm not writing it as an operator, because in here, I've already calculated. I've used the properties of the operator. So I'm just writing this as a matrix times a vector C, and that's given by lambda times a vector C. So when we looked at this yesterday, what we did was simply to say that this is not necessarily zero. If we have a two-body interaction, we can get matrix elements here, which are non-zero. And we actually calculated one of them. One of them is actually listed here. So it means that this block of matrix elements, this specific element, which due to the hermeticity of the Hamiltonian is equal to this matrix element. Then this block here has values which are just given by this quantity here. And if you have 10 particle hole configurations, this block here will contain 10 elements. Does that sound reasonable? So I'm just putting crosses here to indicate that this is not necessarily equal to zero. And then, since we now had a two-body interaction, it means that this guy is also non-zero, possibly non-zero. And if we just rewrite that one, let me just sneak it in here, that specific matrix element, H of phi ij, this is one possible configuration, that was given by just a two-body matrix element, V of AB anti-symmetrized. Then if we have a two-body interaction, we cannot link a Slater determinant which differs by more than two single particle states. So that means that this one, you can just read it off immediately, this is zero. So we will have chains of zeros all the way up here. Then we just proceed here. We have a non-zero matrix element. This is 0, 0, and all the way down here. Now the one particle, one hole can connect to 0 particle, 0 hole, as we saw. It can connect to 2 particle, 2 hole, but it can also connect to 3 particle, 3 hole. Because one of the particle hole pairs here could be the same one as we have in the one particle, one hole state. And then there will only be 2 pairs which differ. But then it has to be 0 here. And this continues like this. We have zeros. And then for the 2 particle, 2 hole, we can connect up to 4 particle, 4 hole. So we will have that one. And then zeros. And this becomes different from 0. And you can see now the pattern here. So it becomes a kind of band diagonal matrix, which goes like this. So clearly, the more particle hole configurations you have, that means the more particles you have, the larger the quantities of zero matrix elements. So we normally say that the Hamiltonian matrix is a sparse matrix. Obviously, if you have 4 particle, 4 hole excitations, there will only be very few blocks of matrix elements which are non-zero. Okay, so the thing which we are going to do today is actually to construct the contribution from every row here. So what I'm going to do now is to rewrite the eigenvalue problem in terms of a solution of a set of nonlinear equations. And the reason for that is that this will link us with the coming many-body theories. So the when you construct this now, you could think of you multiplying this specific row with all the elements in here. So that is one line in this equation which you see here. So let's do line by line and just see what this gives us, because there are some interesting connections here, which I'm going to try to elucidate for you guys. So let's call this a non-practical way. Non-practical way of solving the problem H multiplied with C equal to lambda times C. And before people could diagonalize, this is actually one of the ways by which you would solve an eigenvalue problem. So let's see how we can proceed here. So what I'm going to do now, if you take Schrödinger's equation, what you have is the following. So we have H, if I now rewrite it like minus lambda multiplied with C is equal to 0. Now, this is the same as H minus lambda multiplied with this chain of particle hole excitations which we have. So this would be CH of P. So this is the way we now have expanded everything. So if this is, for instance, the ground state, what we would have then would be H minus E, which is the state we're looking at, times psi 0. And what you see here would be then the expansion in terms of this orthogonal basis for psi 0. Okay? So what I'm going to do now is to take row by row of this Hamiltonian matrix. So what I'm going to do now is just to multiply this one with all the elements here. So let's do that. So we are going to take the multiplication with phi 0 of this specific term here, H minus E times this psi 0. And now I'm going to plug in the different quantities. So what we have first is obviously phi 0, and it's going to contain this C0, and it has H minus E times this phi 0. That's the first term in that expansion, which we have here. So if you look back at the expansion here, the expansion is given now by these different coefficients here. So now I'm plugging in what you see up here, term by term. And that's going to give me the first line of the eigenvalue equation. So I have that, then plus, and now I'm getting a term where I sum over one particle, one hole excitations. So that will contain a term CIA, the unknown coefficient, which you get when you diagonalize. So when you diagonalize, these are your eigenvectors from the diagonalization. And then you simply have to multiply them with the chosen basis you have. So I would get the following now, phi 0 of H, and I'm putting back the operator here, minus E, but now I have this phi of IA, right? So that's this term. That's the first term when I multiply with one particle, one hole. And you can see now that there will be terms which have to be 0 because E is a constant, right? So that means that this term, which you see here, with a constant, and this term has to be 0 because it's an orthogonal basis. So the only thing which will survive here is the term here. And we have already calculated that element. But let's continue now. So the next term would now be the two particle, two hole guys. And then I have an A, B of IJ. And then I have a phi 0 of H minus E times phi of IJ of AB of CIJ, the unknown coefficient. But now something magic happens here. If you go back, so in principle, we have a plus here because we have a free particle, free hole. But if you look back at your matrix here, And let us assume that we're only dealing with a two-body force. So what happens then? It's zero, right? So all the remaining ones are just zero. So it means the first row, when we multiply from the left with phi 0, just to get the matrix elements we need to look at. So the first row of this problem gives us now simply plus plus 0. And this is, since we rewrote the equation like this has to be equal to 0. So this is equal to 0. Now, what I'm going to do now is simply to reshuffle and put on the left this term with E. So if you look at this term here, there's also another thing which is used here, and that is something which is called intermediate normalization. And in that case, what people tend to do, and remember that these are intermediate normalization. And keep in mind now that the wave function is complex. So what's normally done, this is a choice because these coefficients are coefficients we can choose. So that means that I'm going to make a choice here where I have this equal to 1. So that means that this coefficient C0 is equal to 1. Now, when you sum up the other coefficients, the overlaps, they all have to sum up to 1. But since these are complex quantities, there could be an I squared, which is minus 1, times something. So when you add everything up, it still should normalize to 1. But this is a common choice which is used to just get rid of this coefficient C0. And this makes our equations a little bit easier. So if I now move E to the other side, what we have then is phi 0 with H. And this is something we have already calculated. This is the quantity we call for the reference energy. So this is for us, it's just a constant, which we just calculate once and for all. So clearly, if your reference energy is very close to the exact one, it means then that this basis you've chosen, phi 0, is probably pretty close to the exact function. Then we have the next term. And now remember that here, since E is a constant, it means that when I take the overlapping with phi 0 and that one, this simply gives me 0 because the basis is orthogonal. So what I have now is plus, and then I have an IA, and then I have the unknown coefficient CIA, and this is multiplied with a matrix element, phi 0 of H, and then I have my phi IA, like that. And we have already calculated this one. This is nothing but this term I of F of A. So we can plug that in immediately here. Then the next term gives me now a sum of AB, IJ. And then I'm going to have the coefficient Cij, AB. And again, since E is a constant, it means that this term here and the overlap between a state here and this ansatz for the ground state is obviously 0. So the E terms disappear here. So I'm just left with the term of phi 0 of H of phi ij AB. And this is also something which we know. So we can calculate this one or we can tabulate them. This is the same as this anti-symmetrized matrix element, like this. And then what I did, if you now look back at the left-hand side of the equation, I moved this term over to the right-hand side. So that this is actually just equal to E, the exact energy. Now, I don't know the coefficients Cij, AB, and Cia. These are unknown coefficients. So what you see here is that one, I can calculate this one, because if somebody gives me this single particle basis, I can always compute this integral and tabulate it if I want to. I can calculate this quantity. I can obviously calculate this quantity. And the only thing which is left are these unknown parameters which you see here. And clearly also the value for E. So what's common now is actually to reshuffle this one to the left, to the right-hand side, and that defines the correlation energy. So let me just bring up that. So we can rewrite everything in terms of a delta E. And this quantity is in the literature called the correlation energy. And that's going to be equal to the exact energy minus this quantity, which we can calculate, the reference energy. And what we are hoping for is that this term here is as small as possible. And if we rewrite it, this is equal to the sum, since we have only a two-body interaction. If we had a free-body interaction, we would need to link free-body terms as well. That would just complicate things a little bit for us. But the basic structure is what you have here. So this is an I of an F of A plus this term I of B, Ij, C, Ij, A of B. And then we have the matrix elements V of A and B, anti-symmetrized.
So this is a measure of how the approximation.
Yes, yes. Now, all of many-body physics deals with finding these guys here, if you have a wave function-based approach. So this is a kind of overarching message. And you will see later when we now write some of the next equations, because this was the first row. But we need to write out all the rows, right? And then the typical approach which people do is that you solve this equation in an iterative way, which means then that you give a guess for these different coefficients, and then you plug them into the equations, and then you solve the equations, and then you plug these back into the equation for the energy, till this delta E becomes as close to zero as we want to have it. So that's the kind of iterative way you would run the calculations here. If you start with the non-linear solver, because the equations now will be non-linear in these unknown coefficients. And you will see that when we move to the next row. So now we've done the first row in that matrix. And this is a very compact expression for the energy. So if somebody gives you these coefficients, then you have the expression for the energy. So let's go to the next row. So in the next row, what we are doing now, we are picking one of the states, phi of IA, and we are multiplying with all the elements which you have in this row here. So now we are taking this specific row, and we are simply performing the same multiplication again. So in this case, you will see that the free particle, free hole terms will pop up. So when I do the same with a 2-particle 2-hole, you will get a 4-particle 4-hole. When I take the free particle, free hole, there will also be a 5-particle 5-hole, and so on and so on. So that means that gradually, as you write down all the rows, you will get all the different unknown coefficients in the equations you're going to solve. And that's where you also have to make approximations, because solving this equation here is not very efficient from a computational point of view. So I'm doing this from a pedagogical point of view, because this links with other many-body theories. Okay, so let's do that multiplication. So we take that one, multiply with its own row, with a second row. And we want that also to be 0. So if we perform the multiplication here, what we're going to get then is the following. So we are going to get a phi of I of A, and we have multiplied with H minus E. So there's obviously a constant here, phi 0, term with E times phi of I, which is obviously 0 here. So this has to be 0. Okay, so that sounds plausible, right? And then we have the next term, which now contains a sum over the particle Hall states. So I'm labeling that as a BJ sum, because they can be equal to I and A, but they could also be different. So in principle, we have a sum over all the one particle Hall states, And now I have a matrix element of phi IA, and I have H minus E times phi JB. And we have this and then we have the next term, which runs like plus, and now we have a sum of a BC of J of K. So I'm just writing down in a pretty slavish way all the equations here, BC, and then I have a matrix element of phi of A, and then I have H minus E, and then I have my matrix element, which is phi J, no, the state, phi JK of B of C, and plus, but now I also have a free particle free hole term. So I need to have a sum over BCD JKL. There is a coefficient CJKL, a free particle free hole coefficient. And then I have my state phi of I of A of H minus E. And this is multiplied with the state phi JKL of BCD. Now, this term is the last one, because we cannot link a one particle, one hole excitation with a four particle, four hole if we have only a two body interaction. So this is equal to 0 again. Now, you quickly see that the term here, which involves E, has to be 0. The same here has to be 0. But here we have to be a little bit careful. Here it's automatically 0. Here, in case I and A are the same, then we actually get a contribution here. So we have to be a little bit careful. So what we're going to do now is to rewrite this one, this equation. So this is obviously 0. So what we get now when we rewrite it, so let me just do that. So the first term is a phi of IA of H acting on phi 0. So this term here gives us what we calculated before. So this is an I of F of A. So we know that one. We can just plug in the matrix element. But then what I'm going to do now is to extract the term here where B and J are equal to A and I, because then the term with E will be non-zero. So I get a term which goes like phi of I, A, and then I have a H times phi IA multiplied with CIA. And then the term with E, which you see here in this sum here, this term with E, which comes from the term with B and J are equal to I and A. This is something I will move on to the right-hand side of the equation. So this gives me, if I just continue here, this is going to give me a sum over B and J, where J and K are different from I and A. And then I have my phi of IA of H of phi. And now in this case, the diagonal element is obviously not here. So that means that I and A and J and B are different. So the term with E disappears automatically then. And then I have a C of I, C of JB. And then I have the remaining terms, which go like B, C, J of K. And then I have my phi I of A. And now the term with E, the constant one, disappears because these states are different. So I have a JK and then a BC multiplied with the unknown coefficients of JK and BC, plus the final term, which contains BCD, JKL. And then I have a phi of I of A. And all these matrix elements can easily be calculated and just tabulated. And then you will just look them up depending on the indices which you have. This is BCD multiplied with these unknown coefficients, JKL And you see the complexity of the equation here now pops up because the coefficients will come, all the coefficients will pop up row by row when we do the multiplications. But this is now equal to this energy times C of IA. Okay, so there's something interesting now, but I just wanted to write down. So this is just the full equation. And the way you would solve them would be in an iterative way. So you see now that you can isolate the equation with CIA, for instance. So you have CIA here, and you have CIA here. So that means that when you solve it, you see that the energy comes in here. And you quickly see here that this is going to be a set of nonlinear equations. That's rather easy to see. But let's write the next term, the one with a two-body interaction. So let's do the case where we multiply with phi ij AB, like that, times the third row. And what I'm going to do now is simply to set up the kind of equations which we are going to get. So this gives us the following. It's going to give us a sum, a term ij of V of AB, and these are anti-symmetrized matrix elements. We are going to get a sum where we have a two-particle, two-hole state, which links with a one-particle, one-hole state. There's going to be a Kc here, like this. And then we have a phi of ij AB with H, and the term with E disappears because this is also a state which is different from the Brown-Niket. The Brown-Niket states are different. So this should be a K, a state K, and a state C. So this is the one-particle, one-hole excitation, which it links. So this is a two-particle, two-hole with a one-particle, one-hole. And then I'm going to single out a term which is due to the the two-particle, two-hole states being equal. So I'm going to have a Cij of AB, and this is multiplied with a matrix element ij AB of H on this side. And then the one with E, I'm going to put on the right side of the equation of ij of AB. So this matrix element here is also something which can be calculated, and it's going to be given by the reference energy plus a matrix elements which connects AB and ij. But the calculation of that one is actually one of the exercises we're going to look at next week. So now, when we are going to have a sum here of KL, and then we're going to have a sum over C and D. So there's going to be a coefficient CKL, CD, and they have to be different from AB, IJ. And then we have IJ, AB, multiplied with H, and now they are different, which means that in this specific case, we have to be a little bit careful actually, because we can have, so the E term is going to disappear. But here we could have only, let's say, KL, C, and D, only one of them could be different from A, B, and IJ. But I'm going to write it in this more compact way here. So I'm going to have a KL over CD. And then we are going to get a free particle, free hole term. So there will be a sum over CDE. And then I have a KLM. So this is getting a little bit boring, right? Isn't it? Eh? CDE. And then I have H, and this is multiplied with this state of CDE. And this is a free particle, two-hole state, two-particle, two-hole to a free particle, free-hole. And finally, I'm just going to write it like the two-particle, two-hole going to a four-particle, four-hole term. And this is equal to this energy times Cij of AB. Then you would continue now with the fourth row, fifth row, and so on. So you see, this is not a very efficient way of solving the problem. However, it's going to give us a lot of insight about the way different many-body methods function. So let's now assume that we want to start the iteration. So this is normally solved in an iterative way. And many of these many-body methods apply iterative solvers, where you have equations which are non-linear in the unknown coefficients. So this is solved iteratively. So that means that we need a guess. So we would typically have a CIA, and we can call this guess 0. So that's the first iteration. And then we would have a guess Cij, and we're going to assume that this is different from 0. And then we would have a Cijb of 0th iteration, which is different from 0. But then a pretty common choice is to put all the other ones to 0. Because you're assuming that the higher order types of correlations, let's say 3-particle 3-hole, 4-particle 4-hole, can be neglected. That's an assumption we are making. So that means that what we are saying now is that Ij, K, A, B, C, etc., they are all equal to 0. So that's the first iteration. So let's look back at the equations which we have. So the equation for the first row, which is the one we put up here, which is the simplest one, this equation here depends only on Ci, A. So this should actually have an A here, and Cijab. These are the only two unknown ones. If we now look at the next row, what we have is this unknown coefficient here. We obviously have this unknown coefficient and this unknown coefficient. So what's common to do then is to say now the following. If you look at the way we rewrote it, what I'm going to do now is simply to put this one to 0, just as an assumption. I put this one to 0, and I put this one to 0. This is just to get started with the iterative process. So if I do that, you can also, if you want to, you could actually keep this term. That's possible to do, but normally we will put this one to 0. And the only term which we plug in is the first one, the second one, and we take this term here. So when you put these things to 0, I mean, this is very much in an ad hoc way, but there's an interesting result which pops out. So if I do that for the first iteration, so we have then the second row. If we look at that, what we are going to get then is the following. So let me just write this down. So this is the second row here. So I'm going to get an I multiplied with f of A plus the matrix elements phi I of A of H of phi IA multiplied with CIA, and this is equal to E times CIA. Okay, so one of the things which we calculated last week was actually this specific contribution here. So what we found last week is that this term here is equal to this reference energy, E ref, plus, and then we have the A of F of A minus I of F of I. So this is an evaluation which we did last week. So what we are getting then is an equation here where we now have I of F of A. This is just a constant here. And then I have now an E0. So I'm just going to plug in plus alpha of F, no, A of alpha minus I of f of I multiplied with this coefficient CIA, the unknown term. And this is equal to delta E times this coefficient CIA. Okay. And if you go back now, you see that delta E, and this is where you see the nonlinearity of the equations. If you look at delta E is actually given by this term here. So then you see clearly the nonlinearity of the equations. Does that help to see? So this delta E is defined. This is an exact definition. We don't know the coefficients, but now I'm going to set up an iterative scheme where I want to find these coefficients by iteration. So now I'm just setting many elements to 0. So that's just an approximation I make. And then I'm simply saying now that this delta E, which I have, contains C of IA. And that clearly tells you that this is an equation which is nonlinear in the coefficient CIA. And it's going to be nonlinear in the coefficient CIJAB as well. So but now comes a further approximation here, which we can make. So you remember now that this A of F of A, so this is we can actually link this to many-body perturbation theory. And in that case, we would simply take the term which we know, this one, and this is what we called for the unperturbed energies if this basis A is an eigenbasis of that quantity. And then we have a term which now sums over the whole states. So it has a term which runs over matrix elements of the type AJ, V, AJ, anti-symmetrized. So what I'm going to do now is simply in the first iteration, I'm going to put this one to 0. Okay? So you are allowed just to, because we are making approximations, right? So we simply say that these matrix elements A diagonal, A and F with A, is now simply given by the unperturbed energies. Alternatively, if we have a Hartree-Fock basis, we could now, if we don't do that, so we can include it or we can exclude it. So let's say we include it. So let's now take away this one and simply call this term here for an epsilon tilde A, just to distinguish it from epsilon A, which is an eigenvalue of the operator H, if A is an eigenbasis. So that means that we would also have I of F of A of I, which we would write as an epsilon tilde of I. So let's assume now, so what we could say now is that this is, these terms here, they give a modified single particle energy. And we don't, at the moment, we don't distinguish between this E of A and E of A tilde. Now, the next thing we're going to do now is simply to put delta E to 0, just to make life simple. So this is the approximation. So we put delta E to 0, and that means that what we have then is that this coefficient CIA, and then we take a small break. We can rewrite that in terms of this matrix element, F of A divided by this epsilon of H tilde minus epsilon of A tilde. If I do this, if I then plug it back again into the equation for delta E, which now contains this term C of I, what I have then is that my first iteration, so this will be my 0, I would get this state here multiplied with a matrix element. If you go back now, if you look at the expression which we had here, it contains IF of A. So these matrix elements are emission. So I can rewrite that as this one squared divided by epsilon H, epsilon I minus epsilon A tilde, and this is sum IA. But I still haven't defined this AB of IJ, and we're going to do that after the break. So we have this term as well, multiplied with the matrix elements IJ, V of AB, anti-symmetrized. So after the break, we are going to look at how we can approximate this one for the first iteration. So this is what you would plug in for the energy at the first iteration. So after the break, you're going to see that we can write this Cij AB. That's going to be equal to Ij VAB divided, this is the approximation we can make, plus epsilon J tilde minus epsilon A tilde minus epsilon B tilde. So if I plug that in, and this is something we will see towards the end of October, this is many-body perturbation theory to second order in the interaction. So that means if I make this approximation to my iterative scheme, then my first iteration gives me perturbation theory to second order, and you will see that later. So you can actually discuss many of the many-body methods by looking at this set of nonlinear equations, by making specific approximations when you solve things iteratively. So right now you won't see it, but when you plug this in, this will be the same as many-body perturbation theory to second order.
So those are like clever approximations.
Yes.
Because
yeah.
You know, we will see in the future that
yeah.
what they're actually doing is changing just a little bit.
Yeah.
It could be the case that we were messing things up.
Yeah.
But we will see that that's not the case, right?
Yeah. Okay. So this way, if you see the overarching picture with this FCI method, many of the other methods can be interpreted in terms of this eigenvalue problem which we have put up here. So it's a little bit early to see this explicitly, but this term which you see here, like the first term, this is actually what we will get when we do many-body perturbation theory to second order. When you diagonalize, obviously these coefficients may not be equal to this, right? Because they will include more correlations. Because you see the CI's here, they pop up in the equation which you have here. This is the third row, and then they pop up in this equation. And then if you go up here to the first one, they pop up here, and they will continue like that. So what we did now was a very rough approximation, but it gives a nice link with other many-body methods. I went a little bit over time, a little bit deliberately, but obviously we take a longer break then we take a break, so we start a little bit later. So I'm putting the record. So one of the things we are going to come back to is this type of approximation when we begin with many-body perturbation theory. So what I wanted to show you was a non-practical way of solving the equations. Actually, this is more floating point requiring compared with standard diagonalization. So the main message is if you can diagonalize, diagonalize. However, when we begin with many-body perturbation theory, we're actually going to see that many-body perturbation theory to second order is going to give us this equation which you see here, this one. And this equation here is simply going to be given by this coefficient, which has an explicit mathematical form. So the advantage of many-body perturbation theory is that you can calculate the terms order by order. So everything inside is known. Whereas the way we wrote this equation, we have these unknown parameters here. So in a way, this was a kind of digression, but we are going to use this digression when we link with other methods later. The final digression, before we look at exercises for the rest of the day, the final digression deals with the way we solve these equations, because next week we are going to start with another many-body method. So we won't use that much time more on FCI, because FCI is pretty straightforward. So we have Wick's theorem, we can calculate the matrix elements, and if we can set things up and diagonalize, we are done. Now, everything we are going to deal with deals with specific ways of transforming this matrix into more and more diagonal form. So when we are going to do Hartree-Fock theory, you will see then that these matrix elements here will be zeroed out. Then you could think of zeroing out this element and have a method which also takes away this one and that one. That will lead to copper cluster theory. And that means that you will reduce some of the matrix elements to zero by specific transformations. So you can interpret many of the other many-body methods as specific unitary transformations where you make your matrix more and more diagonal. That's the ideal, actually, to make your matrix more and more diagonal. Okay, so the thing I wanted to end now is actually to look at this Lipkin model, which we discussed in one of the exercises. So let's look at that as an example. Now, in one of the exercises in the Lipkin model, you were asked to rewrite the Hamiltonian in terms of the operators for angular momentum. So I don't know how many of you reached that specific part, but you could rewrite the Hamiltonian for the model. So let me just rewrite the Hamiltonian and the model itself. So this is a simple model, but which conveys much of the kind of physics which we will see later for more complicated system. So it's a system where we have a spin equal to -1/2, and this is often written as a spin down state. So this is this level. There is a gap between these states, which we typically call an epsilon. So you can use 0 as a reference point. And then these other states is a spin with +1/2, or just a spin up state. And then in each of these, you can have different single particle states characterized by other quantum numbers. So you could now think of having 1, 2, 3, and 4 particles. This is the case we've been looking at, n equal to 4. And that means that we are going to have slots here, which we can call 1, 2, 3, and 4. And these slots could refer to different quantum numbers. So in this case, we would have P equal to 1, 2, 3, and 4. And we can fill in particles here, like this. That means that we could make an ansatz for the ground state of the system, where we could now think that this phi 0 is now given by A1 dagger, A2 dagger, A3 dagger, and A4 dagger, like that. Then we can think of promoting particles to the higher state. So we are going to make interaction elements, which allows us now to kick one particle, for instance, up to the state with a spin up. So you could now think of making a new Slater determinant. So I'm going just to write this spin up and spin down. And you could now think of taking one of these guys and promote that one up here. So you're bringing in a piece of the Hamiltonian, which allows you to do that. So if we now think of this term, which you see here, this specific term, we could now think of this defining of a Fermi level. And then the states which we can reach above, they can be treated now as one particle, one hole, two particle, two hole, etc. states. So you could now think of having another state. So this would be a new Slater determinant phi of I. And then you could have a state where you have all of them in here, etc. So you can actually look at all the possible combinations. And in this case, what you would have now is that P could be 4, 5, 6, 7, and 8. So these are just slots. So in this specific case with 4 particles and this specific system, we can have 8 slots for the particles, where 4 of the slots refer to spin down, and the other 4 refer to spin up.
At phi 0 there, it should be acting on the vacuum, right?
Yes. So this will be the vacuum. So this is actually acting now on the true vacuum. Now, what we had then was a Hamiltonian. So this is just spin up. This is just to indicate the way you can distribute these particles. And then we had a Hamiltonian, which was now simply given by 1/2 times this parameter epsilon. And then it has a sum over the spin states. So it's -1/2 and +1/2, or plus and minus 1. You can always define that to be plus and minus 1. And then it had sigma. And then we had a creation operator, AP sigma, like this. And then we had an AP sigma here. That's the one body part of the Hamiltonian. And then we defined a new term, which is an interaction term, where we now have a sum over sigma, P, and P prime. So this is going to be an operator which is going to promote one particle, one hole excitations. And you can see that, I don't know how much you did of the exercise. And then we have an A sigma P prime. So we are now, this is not the full Hamiltonian. We actually making an approximation to the full two-body interaction so that we can just create one particle, one hole, and two particle, two hole excitations with this specific model. And that's why we have here a state in the minus spin state. So it can either go from here up there, if this is at a minus state, but it can also go from here and down here. And this sums over plus and minus 1/2. So that means that I can annihilate a state in that specific position, so that has a P prime. And since I have a P prime here and a P prime here, this means that this just kicks a state from one of the spin states down to the other ones, or the other way. And then I have a state here, which now is a minus sigma and P. And then I have a new term. And this runs over sigma, P, and P prime again. But this has now an AP sigma dagger, AP prime, minus sigma, and this has an AP prime of sigma and AP minus sigma. And this is going to be a state which actually translates everything into a two-particle, two-hole state. Now, we can rewrite this Hamiltonian in terms of the operators J squared of JC, the number operator, J plus, and J minus. So I'm just going to give you the answer. Hopefully you got time to do that in the exercises. So this H0 is just this epsilon times JZ. So we defined, let me just give you the definition of these spin operators here. So what we did was actually to define different operators here. So we had the, let me just see, where did I put that? So this operator JZ, just to give you an example, is the sum of a P and sigma, contains sigma, and then it has an AP sigma dagger, AP sigma, just as an example. So when I then write everything down, I had the interaction piece. So what I got then is that the Hamiltonian could be written as an epsilon times JZ. And then I have my two-body term. The first one has a 1/2 of V, and then it contains the operator J plus squared plus J minus squared. And then I have the next piece, which contains this W term, and that contains a J plus and a J minus plus a J minus and a J plus, and this is minus the number operator. And this number operator was also given as a sum of a P and sigma. It simply counts the number of particles which I have. So the thing you can do now when you are setting up your Hamiltonian matrix is now the following. So keep in mind now we could start with a phi 0, which now has a JZ equal to -2. It's going to have a total angular momentum equal to 2. So when we have a total angular momentum equal to 2, we get the JZ equal -2, -1, 0, 1, and 2. That means now that I can actually use the raising and lowering operators in order to construct states with different JZ values, but with the same total J equal to 2. And you know that, so I can now rewrite these states in a more compact way. I'm going to rewrite them like a J and JZ here. So the answers we had for the first state was that we had 2 and -2 here. Now, what I would like to have now is 2 and -1. In order to obtain that, what we would typically do then is that we act with these lowering and raising operators with a state of J and JZ. And we know that this is something which is given by a coefficient as a function of JZ, or plus minus. And this gives us back a state with J and with JZ plus and -1. So I can construct these states. And I assume that you've seen something similar when you took a course in quantum mechanics, the raising and lowering operators. So this term which you see here has actually a specific expression, which is J times J plus 1 minus M of M plus 1. And this acts on the state with J and JZ plus -1. And then what we also have, if I look at the Hamiltonian, I can now calculate my Hamiltonian matrix elements with JZ prime. So it has to be diagonal in that because we showed that Hamiltonian commutes with J squared. So that's one of the things we found in the exercise. So if I take H and J squared, that is equal to 0. So that means that J itself is a good quantum number. So that means I just need to set up my Hamiltonian matrix between these different states. And this is going to give me, for the first state, it's just going to, for the operator J0, it's just going to give me JZ times a Kronecker delta with JZ prime and JZ. Then I have my term with V divided by 2. So when I do the algebra here, I'm going to get this term. So this, there's a missing thing here. So it's a plus minus there. Sorry for that. I'm going to get this coefficient C of JC of plus, and then I have a C of a plus operator of JC prime and JC plus 1. And then I have a delta of JC prime with JC plus 1. And then I have a plus, a C minus JC, and then a C JC minus 1. multiplied with a delta JC prime, and this is MJC minus 1. So that's this term. And then I have a similar one for the next term when I put in all the equations. When I do the algebra here with the creation and with this lowering and raising operators, I'm going to get the coefficient C of JC minus 1 plus of CJC. And this is minus. And then I have a delta of JC prime plus a C of JC. I hope I'm doing this correctly here. JC minus 1 of minus, and then I have a delta JC prime. And then I have the number operator, which simply gives me the number of particles, which is 4, n, which is 4 in our case. And then I have a delta JC prime. Then this gives me a Hamiltonian matrix since I'm going to have 5 states. Since I have a JC equal to 2 here, which is the maximum value I can get. So the JC equal minus 2 is the minimum value I can get. JC is equal to 2 is the maximum value I can get. And if I then follow the rules for angular momentum, that means that J has to be equal to 2. So I can then set up my Hamiltonian matrix, which then becomes equal to the following. So I have a 2 epsilon, I have a 0, and then I have a square root of 6 times V, and then 0 and 0. Then I get 0, 0, 0, and 0. I have an epsilon plus 3 times this W. I have 0, 3 times V, and then I have 0. I have 4 times W. I have 0, and then I get a term which is 6 times V, 0, 0, 0, and then I have 0 and 0, and this is minus epsilon plus 3W, 0, minus 2 times epsilon. And minus 2 times epsilon is the one which we have from the lowest line state. So in this kind of notation which we have, this would now correspond to a state where we have a A5, A6, A7, A8 dagger acting on the vacuum state. Whereas this one corresponds to us having placed all the particles in the lowest lying state. So the way I've organized the matrix here now is in terms of the highest JC value. So this corresponds to JC equal to plus 2. This corresponds to JC equal minus 2. And the other ones would be JC equal minus 1, JC equal 0, JC equal to plus 1, and so on. And now we can plug in values and diagonalize. So we can have some, there are some simple cases which we can discuss now. So we can put this epsilon equal to 2, and then we can put this V to minus, minus 1/3. And then I can put W to minus 1 divided by 4. So if I diagonalize them, I'm going to get specific eigenvalues. So I will get the lowest eigenvalue, E4, which is equal to minus 4.21 something. That's the lowest lying state. Now, what we're going to see there is that the coefficients of the wave function, so it's going to have 5 coefficients. So there will be one coefficient which now links with a, so if we look at this psi 0, it will have a C0 times phi 0 plus a C1 times phi 1 and all the way up to C4 of phi 4. So we said that this phi 0 is the state where all the states are in the lowest state here. Now, if you look at this specific diagonalization, you will find that C0, its value is 0.97. The coefficient for C4, which is that mixture with the state where you have flipped up all the single particle states, that coefficient is actually equal to 0.003. So that's very small. The coefficient C1 is equal to the coefficient C3, and that's equal to 0. So there's no admixture, and you can see that immediately from the way the matrix elements look like. And then you have a C2, which also has a very small and tiny coefficients. So when you square these, it means that the probability of being, in this specific case, when you're looking at the ground state, what it simply tells you when you look at these coefficients is that the probability of being in the ground state is pretty high. So the admixture from the other states is small. So what we would say then is the approximation we would get when we look at the energy, since epsilon is 2, we see now that this state which we have here is -4, and that's pretty close to the exact result from diagonalization. And this is simply due to the fact that the interaction elements are small. So this single particle piece is much larger than the interaction matrix elements. So when the interaction is weak, it means that your basis, the one you've chosen, is actually a pretty good approximation to the ground state. So what you see here is actually the phi 0 to a decent approximation is actually proportional with C0 times phi 0 to a pretty good approximation. And that's simply reflected in the fact that the interaction is weak. If, on the other hand, if we pick a stronger interaction, then you will see that this admixture becomes larger, and then the description of the lowest lying state may not have this state here as the dominant state. So in this specific case, we can actually already see that from the Hamiltonian matrix and the values here. And when we diagonalize, we see immediately that this -4, the case with no interaction, is pretty close to the exact value. So you can get a lot of insight about the role of correlations and the goodness of your computational basis. So our computational basis is this one, and we see very clearly here that this computational basis is very good when the interaction is weak and in a way that is expected. When we now, and we're going to look at that next week, when we turn on the interaction and make it stronger, we may, so changing the values, we could change V to -4 divided by 3. We could put W to -1, for instance, and just keep epsilon equal 2. Then we are going to get a much stronger admixture between these computational base systems. So there's a lot of interesting analysis and insights we can get from a simple diagonalization problem. Okay, I'm going to stop today here, and then next week we can wrap up this discussion about the